Hi everyone, my name is Abigail Snortland. I'm a third-year PhD student at the University of Washington, and I am part of the Pacific Marine Energy Center. Today I'm going to be talking about the influence of near blade hydrodynamics on crossflow turbine performance. So the overall goal behind this project is to directly compare phase average crossflow turbine performance data with phase-specific near blade hydrodynamics, which I capture using a technique known as particle image velocimetry, or PIV. This technique allows me to experimentally and non-invasively capture 2D planar flow fields of our system. The key phrasing here is phase specific. So much of the work up until this point that has actually compared turbine flow features to turbine performance has been done on a time averaged basis. And this type of analysis fails to directly compare the crossflow near blade hydrodynamic features in the flow to their impacts on turbine performance. And that type of analysis is essential for better understanding of blade fatigue, for being able to develop better blade designs and control strategies. So that's the overall goal of this project, is to directly compare the phase average flow features with the phase average performance enforcing. So this is crossflow turbine, so the axis of rotation is perpendicular to the inflow, and we define a 0 degree azimuthal position as when the tangential velocity of the blade is facing directly upstream. So the first step of this process was to gather the performance information. And so our turbine looks a bit funky because it has oversized clear acrylic plates that were to aid in the PIV imaging. And this is because I mount the camera below the turbine and look up underneath the turbine. And I'm operating under constant speed control, so I take performance data for a range of rotation rates which correspond to different tip speed ratios. And the tip speed ratio is simply a ratio between the tangential velocity of the turbine blade to the free stream velocity. And through these experiments, I calculate the coefficient of performance, which is a ratio between the mechanical power produced by the turbine to the hydrodynamic power available in the flow. And you can plot this in a time average sense over the range of tip speed ratios tested, and you get a curve like this. However, for my turbine, I have those large acrylic plates, so there's a lot of parasitic drag from the support structure. And I'm specifically interested in tying the blade-specific flow features to the blade-specific performance. And so I want to be able to isolate the actual blade level forcing. And so to do that, I first take a performance sweep of the full turbine. Then I do the same thing for just the support structures, so just those big plates. And then I can subtract out the effects from the support structure to produce a time average curve for just the blade level performance. And it's from this curve that I determined the two tip speed ratios, which I looked at further with PIV. So the first is a poor performing case, which corresponds to a tip speed ratio of 1.1. And the second is a well-performing case, which corresponds to a tip speed ratio of 1.9. So if we take this time average curve and we expand it out into all of the phase averages, we can see that there's a phase shift and amplification of the maximum performance peak with an increase in tip speed ratio. One, because lower tip speed ratios will reach dynamic stall earlier in the cycle, but also because they're operating at lower rotation rates, which means they produce less power. But this doesn't exactly clearly explain the differences in the minimum performance regions. Specifically, if we highlight the well-performing case, tip speed ratio of 1.9, and the poor-performing case, tip speed ratio of 1.1, we see that the 1.9 case has a broad maximum performance peak, but in a narrow minimum performance peak, while in contrast, the 1.1 case has more of a minimum performance trough that extends most of the turbine rotation. So I'm going to look at these cases closer in PIV in a second, but first I want to go through what I call the anatomy of the frame just to orient everyone. So the background of all the plots you're about to see is contours of normalized swirling strength, and swirling strength is simply a criterion on top of the velocity gradient that says a vortex can only be present if the eigenvalues of the velocity gradient are imaginary. And this essentially is separating areas where a vortex is present from areas of pure shear. The flow in all of these plots is coming from left to right. Additionally, I split up the full turbine sweep into two parts, the first being the upstream sweep and the second being the downstream sweep. Also, I'm imaging from below and I'm imaging at the midplane of the turbine, but we have some interesting shadows in the fields. And so this corresponds to the base of the center shaft. The shaft has a corresponding shadow. This is the bottom face of the blade and its corresponding shadow. On top of all of this are the normalized velocity magnitude vectors. And these vectors are colored yellow to pink to signify areas that are slower than the free stream velocity, and blue to green in areas that are faster than the free stream velocity. So starting with our well-performing case, the 1.9 case, this flow on the upstream sweep is characterized by attached flow for most of it. We don't see the formation of leading edge or trailing edge vortices until much later in the sweep, and they're very small. And these vortices are shed quickly after they are formed as the blade transitions into the downstream sweep. Now moving on to the downstream sweep, we can see that the blade moves quickly away from those shed vortices. So not only are they shed quickly after formation, but the blade moves away from them quickly. But the blade still has the chance to interact with the vortex shed from the previous blade cycle, and this is because the tangential velocity of the blade is so much faster than the free stream velocity. Importantly, the blade spends most of the sweep in a very low velocity region, and the flow appears to recover early on in the downstream sweep and appears fully recovered by the time the blade is traversing back into the upstream sweep. In contrast, we're going to look at the entire sweep, so both upstream and downstream sweeps of the 1.1R poor performance case. Probably the most obvious thing here is that the vortex generation is much more energetic than for the 1.9 case, and the vortices form earlier on in the cycle. And this is all consistent with blades at lower tip speed ratios reaching dynamic stall earlier in the cycle. Those vortices remain near the blade for much longer than for the 1.9 case, and the blade is stalled or appears stalled for the entirety of the downstream sweep. Additionally, that blade during the downstream sweep exists in a higher velocity region than for the 1.9 case. But anyway, moving on, I want to directly compare these two cases. So to do that, we're first going to look at the individual phases of maximum performance. So for the 1.1 case, our poor performing case, we can see that the vortices are just forming on the upstream blade, but the downstream blade appears completely stalled. In contrast, for 1.9, the flow appears to be attached on both blades, and the blade in the downstream region is in a low velocity region and likely is producing little drag. Notably, the phase of peak performance does not correspond to that where the leading edge vortex is the strongest, thereby suggesting that the downstream blade is important. Moving on to looking at the phases of minimum performance, we can see for the 1.1 case that the downstream blade is deeply stalled and re-entering a region of higher velocity, so it probably has a lot of parasitic drag. While on the upstream blade, the leading edge and trailing edge vortices, while separated, are still close to the blade and therefore might be contributing a little bit to lift or just a lot of drag. Either this is amplified or counteracted by the drag on the downstream blade. And since those vortices remain on the blade for a long time, they might explain why the minimum performance region is more of a long trough for 1.1. For 1.9, the upstream blade appears to be in fully attached flow and is at a low nominal angle of attack, while the downstream blade is stalled and still influenced by those previously shed vortices, but they've translated past the trailing edge of the blade, signifying a sharp drop-off in lift production, and this might explain why that minimum performance peak is so narrow. So overall, the severity, duration, and phase of dynamic stall on the blades may explain the narrowing of the minimum performance peak for that high performance case. So in conclusion, the near blade hydrodynamics clearly depends strongly on both the tip speed ratio and the blade at smooth position. The duration, severity, and phase of flow reversal and detachment on the blades appears crucial to overall turbine performance. In fact, the blade is in dynamic stall for most of the rotation for the low performance case, while only a small part of the rotation for the high performance case. Interestingly, the phase of maximum performance and that of where the strongest leading edge vortex is present are not the same, signifying that the downstream blade dynamics may have a large impact on performance. So all of those results pertain to some experiments I did about 2 years ago, and were all taken at the turbine midplane. And this January, I was able to wrap up an experimental campaign where I took 6 different span-wise planes of PIV data. And this was made possible because I motorized both the laser table and the camera below the turbine, and so I could move them up and down to capture those 6 different planes. In addition to the 6 different planes, I also took a wide field of view and a narrow field of view. The narrow field of view is intended to better understand and see the dynamics of dynamic stall that are specific to crossflow turbines and better understand those mechanisms. And with all of this information, I hope to have a better detailed view of dynamic stall and how that impacts turbine performance, understand the span-wise variability in the hydrodynamics. I want to calculate the actual angle of attack and relative velocity values from my experimental data. And all of this together, I'm hoping to use this to investigate the impacts and importance of different flow features on turbine forcing and performance. So with that, I would like to thank you all for watching, and I hope to see many of you in the panel discussion session on Thursday, April 29th. So this is session 5T. Tidal river and ocean current technology. And I hope to answer lots of questions there. So thank you very much.